Okay, then let me briefly introduce Markus Heinrich, a friend of the family who will present work with two other friends of the family, namely with Ingo and Martin, who are both PhD students here in the group, on a topic that's also close to our heart, obviously, on randomized benchmarking in the flavor of general guarantees for randomized benchmarking with random quantum circuits. So thanks for coming, and the stage is all yours.
Yeah, thank you for the nice introduction, and thank you for having me here. You basically already said everything that I want to say. So the title, my collaborators. So here's also the archive link. You can also Google it. And I also want to shortly mention that if you like this talk, you can see it again at the QAP. Likely, but in a shorter form. So maybe just pay attention here. Anyway, so the topic of this talk fits into what people call quantum system characterization. So what do we want to do? We want to characterize quantum devices, and we do this by performing measurements on the system to obtain information. And we want to do this in some kind of on a logical level, so that we obtain information independent on the platform dependent details. And why are we doing this? So, I mean, first goal is that we want to build trusts in our quantum system, right? We want to show that we actually did something that did the thing that we claim to do, and not something completely different. Of course, we also want to learn what we actually did, and we want to characterize the errors, for instance, in the quantum gates that we applied. And in the end, we also want to benchmark our systems. And so we want to find out, or we want to design a benchmark that tells us how good were we and how good are the others, and we want to compare. And so there's so I stole this from Martin's slides and some of them too small, sorry. So there's a whole slew of characterization protocols. It's not so important what's written there. So there's a whole slew of characterization protocols, and you can distinguish them basically by how much information you gain from the protocol and how much measurements do you have to do to get the information. And normally it means that if you want to have if you want to have a lot of information, you also have to do a lot of measurements. And also randomized benchmarking sits on this side of the spectrum. So you only get very little information, but you also don't need that many measurements. So this is what this talk is about. Yeah, sorry for the size. So what's the idea of randomized benchmarking? So in some sense, we want to perform a fancy identity on our system. And we want to do this in a way where you can vary the circuit depth of this fancy identity. So this means that what we do is we apply some unitaries. We want to do M. And M is a parameter. And then in the end, we invert the sequence of unitaries using an inversion gate. So ideally, we have done nothing, right? But the point is that in realistic systems, we of course find noise, and we kind of expect that the longer we make the sequence length M, the more the noise stacks and piles up, and we will see this in a decrease of if you measure in the end, basically we see this in a decreased probability of finding the initial state again. And actually, if you do such an experiment, you get a signal like this. So everything I show is in log scale. So depending on the sequence length M, we will see exponential decay. And we can fit this exponential decay, we get a rate R, and this rate is a quantifier of our performance. So basically, in an ideal setting, we'll just get one, constant. But basically, the worse our gates are, the faster the decay is for the same. And that's basically the interpretation of this R. And so the standard setting for randomized benchmarking is the case where you take these U's who come from the Clifford group, the n-qubit Clifford group. And in this standard setting, you can prove a lot. Yeah, so you can have under a wide range, very general assumptions, you can prove that you get such a signal, like an exponential decay. And moreover, using Cliffords has an advantage over using, for instance, random unitaries or something, namely the inversion gate is Clifford itself because it's a group. And the nice thing about Cliffords is that you can efficiently compute group operations. You can efficiently compute the inverse gate. And moreover, what's also important is that the inverse gate has a depth which is independent of m. So it's independent on how many unitaries you applied before. And this is kind of like, in principle, a nice setting where the things work well. So, but the problem is that nobody's doing that. So, and why is nobody doing that? Except maybe for a single qubit. The reason is that multi-qubit gates, multi-qubit Clifford gates, I mean, they have efficient depth. They have like basically linear depth. But in practice, this is too deep. It just means that basically, if you go to more than 3 qubits, your multi-qubit gates, multi-qubit Clifford gates are very noisy. And this means that basically, in principle, the experiment still works, but your decay will be so fast that basically after a few iterations, you will be in a regime where the signal to noise ratio is like terrible. And you will not be able to extract any meaningful information. Also, the sampling complexity will go up as hell, because basically, if you want to estimate like exponentially small signal, well, it sucks. Okay. Then okay, you can argue that okay, fine, if multi-qubit Clifford gates are too deep, then we just do something simpler. Yeah, maybe like I don't know, some C-naughts or like something very simple with I don't know, constant depth. Yeah, but even if you do this, you still have the inversion gate. The inversion gate is like the product of all the fixes you did before, and in general, this inverse gate will still have like a linear depth. In general, still destroy this setting basically. But besides like this noise aspects, there is even something worse, which is kind of overlooked in my opinion. Namely the question, what are we actually benchmarking here? And nobody can do multi-qubit Clifford gates natively on their device. You have to compile them into, for instance, 2-qubit gates. And well, depending on your platform, where you can do 2-qubit gates, or you can do n-qubit entangling gates, like the depth of this like component is like completely different, right? Like you know, experiment A can do it in like depth, experiment B can do it in depth 20. So what you're actually benchmarking is how good the compiler is. It's not really platform independent, right? So is this actually meaningful to benchmark mostly a compiler? And also, why do you use Clifford gates? Why do you use multi-qubit Clifford gates? Is it something that prominently features in quantum algorithms? I don't think so. But if you're doing mostly non-Clifford gates anyway, or like simpler gates, why do you benchmark multi-qubit Clifford gates? Good. That being said, what should we do instead? And the interesting thing is that it's already done instead. Maybe not for the like last reason, but it's actually what people are doing. It's like an experiment that basically runs as follows. You pick some gates from some discrete or continuous gate set. These are mostly native gates, nothing that you can do via simple pulses or something like this. Then you make a random circuit out of them. Then you increase the depth of these circuits. In the end, you can either invert the sequence or you do something else, namely you do some more or less heuristic post-processing of the data without inversion. Then in the end, you fit exponential decay. You report the decay rate, and you're done. Okay, so what's the problem with this approach? Well, there is no theoretical guarantee here a priori that it works.
Also, there is no end gate from the group, right?
Well, there is no end gate at all. Yep. And the point is that, just because you saw an exponential decay in an experiment doesn't mean that you have done anything meaningful. It's actually pretty hard to not get exponential decays if you do something along these lines. You have to really, really, really try hard and find special cases where you can find something else. So basically, observing an exponential decay doesn't mean that things are well. What we need is we need some kind of general theory that explains why you get an exponential decay, where it comes from. Otherwise, this is just meaningless data. In our paper, I think we closed this gap quite well. So there are a few works that basically went into the same direction, namely the paper by Jonas Helsen and people from the group. And there was also a paper by some researchers from Alibaba that also went into the same direction. And so in this overview, I marked everything in blue, which is covered in these papers, and everything in green, which we didn't. So for our protocol, you can pick gates from any compact group. So you can do whatever discrete continuous gate sets, you can do fermions, whatever. Yeah? Then what you do is you can use arbitrary measure on this group to build, for instance, random circuits out of these gates. We don't need inversion. And we propose, or we show that there's like a meaningful way of doing post-processing to basically extract meaningful exponential decays.
Someone's not muted.
Sorry?
Someone is not muted.
Ah.
Yeah, well.
Okay, I think we have very minimal assumptions for all of this. We analyze, for this very general setting, we analyze the required circuit depth and give like guarantees on this. And we give general sampling complexity guarantees. Everything works for basically any complex group and every measure that we have. Only assumption that we have on the measure is that it's kind of gapped.
Can I ask a question?
Yeah.
Do you mean here any gate, or you need to implement a group? Someone from a specific group. You can be any group, but need to be a group. I mean here.
So what we need is we pick a way of sampling from some group. That's what I mean. And this sampling should be, it has to fulfill some minimal assumptions in the sense that basically, I don't know, that you kind of universal for that group if you want. Yeah. So basically, that if you do a random walk in this way, that you cover the whole group. Because I don't know, if you sample from a subgroup and you claim you have sampled from the big group, you don't cover the whole big group, but then you could also start with the subgroup instead. But
also on a similar standpoint. So compact group is green, right? So in the blue Helsen paper, we also look at arbitrary groups.
Finite groups, yeah. I mean, it's very easy to show for compact groups. It's basically the same for compact groups.
So the green part is you go from finite groups to compact groups.
Yeah, but I wouldn't say that this is. I mean, this is not like a super big step. I mean, like representation theory for compact groups is basically the same as for finite groups.
I see. Okay, so that's kind of okay. Yeah.
So the thing is just basically that this allows us to design protocols for. I mean, it covers match gates, for instance, and stuff like this, right?
Okay.
And also, I mean, currently also like looking into, for instance, the compact selected group in bosonic setting, for instance, like passive transformations.
Which would be basically like UN, right? There is more UN.
Yeah, exactly. That's in compact.
Yeah, I understand.
So yeah. But you're right. I think this is like
okay. No, that's what I understand. Thank you. Blue green.
Blue green. Yeah. I think there was also a question back there. No?
Yeah. My question answered by point 2, but then I still have a question. So I was wondering whether the measure need to be the Haar measure.
No,
but
I mean, it is not a Haar measure.
Okay, but then when it starts, like when I take like a sequence of measures and I start to concentrate more and more, then something has to become worse, right?
Or something has to become
something has to become worse. Like I mean, when I start to sample essentially only a subgroup, for instance.
Yeah, these guarantees depend on choice of measure. Yeah, but it depends explicitly on choice of measure. And if you decide to sample in a really bad way, then the guarantees will be bad.
Yeah,
but it's up to you. Yeah. Right. Okay, so this is like only really overview, right? I mean, we go into details in like 2 steps. I think that medium level of details and like a bit more detail. Yeah. Okay. Examples. Forgot about this. So basically can you see this even? I mean, okay. So there's linear causality benchmarking, which falls naturally under this class of protocols. There's things called correlated and simultaneous RB that fall under this class. There's polytomography, match rate benchmarking, and a lot more actually. And so it's pretty general, and it basically it generalizes and unifies a lot of things. Not that it's before.
So we call our paper the mother of our RV schemes. That's like the grandmother.
Yeah, indeed.
But we guilty of that too all the time. Like we have the most general approach, and then we write another paper, and then you at the end.
Yeah, indeed. Yeah, I think the major difference to your paper is basically the assumptions on the measure.
Yeah, of course.
Okay, so how does it work? We call it filter randomized benchmarking. That's not the name we came up with, but it's up to you. As in the Helton and Alt paper. And so basically the idea is that for most practical purposes, this will be how such a protocol looks like. You choose a random survey, for instance, brickworks. Yeah. And then you fill the bricks with like I don't know some random gates that you like. And then you iterate the brickwork, you add more layers. And now an important fact plays in, namely, in this way you will generate a group. And it's so basically if you take random circles and then you take the span, it will be a group. And it's basically the minimal group in that you can have until where these things happen, so to say. Yeah. We also start the other way around. But anyway, the representation theory of this group will play a role. And so we look at the representation of this group on linear operators, and there it decomposes into errors. So I don't know, if you have a universal random circuit, then basically you will only find two errors, namely the trivial one and the traceless error. And then you will focus on the traceless error because the trivial one is so interesting usually. But if you take smaller groups, then there will be more errors. For instance, if you take a poly group, then you have exponentially many errors. And these errors play a role. But namely for any error, we do a post-processing. And but of the same data. So we only have to collect data once, and then we can do classical post-processing as often as we want. And then we get the curve, depending on the depth of this random circuit. And without noise, nothing really spectacular happens. You will find that the signal converges to a constant. But if you add noise, then you will find that the signal converges to an exponential decay. And what we do is basically, you see there is something non-trivial going on in the beginning.
But this is it's a bit hard to read. This is a logarithmic.
It's logarithmic.
Okay.
Yeah. So in the beginning, there's something non-trivial going on, but after like a small amount of time, you will be basically in this exponential decay regime, and we give bounds when this happens. And from this on, you can just fit this signal and get an exponential decay. And that's basically the idea. And everything here is that robust as it should be for
And if you're too noisy, you're anyway doomed.
If you're too noisy, you will find like a very fast decay. But in principle, so we have some conditions on the noise. So the noise has to be sufficiently small in some sense. And then this analysis works. If you're not in this regime, then something else happens. But I can talk about this, somewhat.
And you say you have the conditions on, like you have bounds on the depth, on the minimal depth where this behavior kind of.
Yeah, exactly. I covered this in one or two slides.
Okay, no.
Exactly. So that's basically the overview how the program looks like. And so how does it work? Why does it work? And so, okay, so we have this error decomposition, and like this representation, we call it as omega for notational purposes. And so we have a measure from which we sample, let's call that nu. And so on like an abstract pictorial level, that's what happens, right? We have the initial state, we sample some GIs from this method, and then in the end we do basis measurement. And this will define a bond probability. And what we then do is basically we use the clicks in the experiment to estimate a function. And this function we call capital F lambda, and it's can you read this? It's its expectation value of a function smaller f lambda. And if you write this out, then this bond probability enters in the expectation value. And this small f lambda function is what we call a filter function, and that's why we call it filter randomized measure. And in principle, you can make different choices for this filter function, and Jens has also like written a paper on different choices of these functions. And so what we choose this function here to be is basically a bond probability in the noiseless setting. So it's basically what you would get if there would be no noise. But there are some additional terms. Namely, one is this P lambda, which is the protector, onto the error lambda. So that's the thing that basically filters out the error component. And then there's like an additional super operator that is called S, and it's what we call frame operator. And it's the thing that basically always pops up in shadow estimation, for instance, but we will talk about this later. And yeah, that's basically how it works. And then,
sorry, before you go on, what's the choice that you can make with respect to the filter function?
I mean, in principle, you could use any function, right? It's like it's kind of linear post-processing of the data, and it's basically kind of building an overlap with the bond probabilities, and you can choose any function there, yeah? But then you have to prove that it does something. And so for this choice, we can prove that something meaningful happens, and there are other choices. For instance, in this paper by Jens and others, where other things happen. Yeah? And so in principle, you can also leave out this P lambda there, then you will get the sum over all the error contributions, and you will see a superposition of exponential decays. So that's what you normally see in standard RP. You see the superposition of exponential decays, but you don't know. But it's hard to isolate an individual one then. And you also don't know which decay corresponds to which error and so on. So that's why we have this filtered approach.
I mean, I mentioned the paper with Emilio,
yeah.
The first one with and Albert Werner.
Yeah.
I mean, that was finished, and then it took us like 1.5 to 2 more years to get it out for that problem.
Yeah.
To isolate poles. Yeah,
indeed. It's in general it's complicated to find these decays. Yeah. But now here we only have one, which is nice.
And you change the filter function by changing S, or
no? S is basically fixed.
What is not fixed?
The P lambda. So we just go through all errors, or these errors that we are interested in. Nobody forces us to look at all of them.
Okay.
And yeah.
Okay. So every F lambda there's no choice. F lambda is defined in this way, and that's it.
Yeah, for the purpose of the report, this is fixed.
Okay, but the way you change it is you can.
Yeah. So basically, in our paper, we discussed alternative choices, but I will come to this in the like last slide. Okay. Then okay, now I will tell you about the circuit depth. So basically, what we need. Just, I have to introduce this because otherwise the equation doesn't make sense. So what we need is the spectral gap of this measure. So that's which we assume to be larger than 0. And that's basically like sufficient criterion for the measure to converge to the Hahn measure, basically. And then we also need the error dimension. And then we can formulate like a result, maybe that our signal is close to an exponential decay. If we choose the circuit depth basically larger than the inverse spectral gap times the logarithm of the dimension of the error. That's basically the result. And this epsilon here is the approximation error here in this sign.
Wait. So that's a condition on the length of the
So basically, it's the condition on the number of layers in the circuit, like this one.
until the set when the set's in.
Yeah.
But of course there must be further assumptions. I mean, of course that the reference representation is close to the ideal representation. Like I mean that in diamond norm you are so close to the.
Yeah, we have basically this assumption that basically if you average the implementation function over like this pattern mu, that basically then this is close to the average over the average of the implementation.
But that's not.
So this
You need on top of that, right?
Yeah.
As we do need as well. I mean that was also part of.
The point is basically if the noise becomes too strong, you will not see the noise decay, but you will only see the design decay.
Because exactly that's what I meant earlier with the strong noise, because they crashes down and you see this, but then there's no kind of long tail.
No, exactly. You have an assumption on the noise strength, but
Okay.
you can just.
Yeah.
What is on the y-axis again?
That's the F lambda basically on the y-axis here.
Wonderful.
I mean, you said we need more data when there is like more noise because signal to noise ratio. So it's like a low value here. Does it mean you need more samples to see it? Or is this something else?
Well, I haven't talked about like how many samples you need so far. I will talk about this in a second.
So this is the picture shows the filter function of
Yes,
the
exactly.
period.
So in green, there's like basically noise free case, and in blue, there's noise.
Okay. Thanks.
And maybe how can I get a feeling for this scaling in a way? Like, how does it come? Let's say if you had a Clifford.
Does it help?
Yes.
Okay. So basically, if you have a two design, so if your group is a two design, means for instance, you have universal random circuit, and the group will be dense in the unitary group, or in the Clifford group, and use Friedberg circuits like in this picture here, then you can give like very concrete bounds. Yeah, and so meaning here it's something like 10n or so. Yeah.
But is that not like is that better scaling than saying that you then like okay, if I wanted to pick a random Clifford element from the
It's better. It's better because for two reasons. First, the 5 there can be improved because we just that's bound on the spectral gap of Friedberg circuits that we know, and just in the end, like after like almost 2 years, I was a bit lazy to improve that constant. And second, it's basically it just means that m has to be larger than this, so we can go to m plus 1, m plus 2, m plus 3, m plus 4. And for Cliffords, every individual Clifford has that n. And so you can go to n, 2n, 3n, 4n, 5n.
Right.
See? And that's basically the but also like we have a more fair comparison actually in the paper between Cliffords and random circuits. But it's actually hard to in terms of scaling, it's not so easy to beat that. Yeah. So sublinear to have sublinear scaling with this approach is not I think probably not possible. I mean I sketched like in a second. I sketched a few ideas how you could get sublinear scaling, but we have to do something more. And the reason is basically this initial behavior here. Yeah. Right. Okay. So then I also want to talk a bit about the Simon complexity because we also have some guarantees here. So in the post-processing, we basically estimate this capital F lambda here as the expectation value of the small f lambda. And we can do this in many ways. Yeah. So what we do here is we consider a single shot estimator, meaning that basically you sample a random circuit and you measure it once. Then you sample another, you measure it once. Yeah. Now you can also say, why don't I measure from the same random circuit like 1,000 times? You could do this, and expectation will be the same, but the variance will be higher. Yeah? And
Is this so?
There's a nice paper by Michael Walter and Jonas Helsen from like December that basically addresses this question, and we also have it in the paper. There's an additional term popping up if you sample multiple times from the same random circuit, which increases the variance, and you can neglect this term if you have a large dimension. That's why basically for instance, in the supremacy experiments, they sample a lot from the same circuit, and that works because they have 50 something qubits, so the dimension is super huge, and there's basically no difference whether you sample once or 5,000 times from the same circuit.
So like as you probably know, like with your PhD supervisor and Steve and so on, we looked a long time ago at like this compressed density tomography where we asked the same question, like do you take the same, like you pay like €1 per shot, and what you have 1,000 euros, what do you do? Like do you try to measure a few observables nicely, or just all over mainly all over the place, and that didn't make any difference?
Yeah, here it makes a difference.
What is better?
I mean, it's always better to use a signature estimator from sample complexity point of view, just because you can prove that the variance is lower. But of course, there are also other things that play into account. I mean, preparing a random circuit and measuring doesn't have much of an overhead nowadays. Basically, if everything is automated, I think doesn't make much of a difference to if you whether you sample like 1,000 times from the same circuit or once, like from just from like addressing the quantum computer. But I mean, you have to do the post processing, so you have to simulate every random circuit that you draw, basically, and that makes a difference, right? It's much easier to only draw like a couple of random circuits and simulate those instead of having to simulate all of them. So that makes a difference. And so there are different regimes. Like if you have like a low dimension, low number of qubits, you should use the single part estimator, but then also simulating is not super difficult. And if your dimension goes up, simulating becomes more difficult, but you can sample multiple times from the same circuit.
But it also depends on the architecture, right? I mean, if having a new random circuit means going to the clean room and then spending $500,000 and waiting for 10 weeks, and
So we kind of restricted to this estimator, but in principle, we could also do a similar analysis for the other estimator. It just becomes more messy. Yeah, it just becomes more messy. So here we have a kind of clean result, namely, basically, if we choose the circuit depth more or less twice as large as before, then we can basically guarantee how many samples are sufficient for estimation. Yeah. And here is a bit of like a convoluted statement, I think. So imagine that you know how many samples you have to take if everything is noise free and you sample from the harmonizer. That's something that you often can compute by evaluating R integrals. And if you know this number and ideal, then basically in the noise case, so if you have some general gate dependent noise and you sample not from the harmonizer but like in some weird way, then you at most get like some small correction basically with this ideal setting. Yeah, and this alpha here pops up here unless it's like
the number of qubits does not enter.
It enters through the Europe dimension usually, and sometimes also through the spectral gap.
Okay.
But you can choose the spectral gap to be constant. We use, for instance, spectral gap circuits, and then the log will be log t squared basically is for log 4n, like no 1.75. Anyway, yeah, so there it enters.
And did you plug in the numbers for some typical situations?
Yep.
Where we come to that? Or
I mean,
more or less?
There. So in the paper we have more examples, yeah, but so here slides are kind of like finite, papers are somehow not.
What is n ideal is the same? That's 3. Okay,
Yeah,
then you have this.
So basically, if you have a unitary field design, it's kind of well known that you can like do the high integrals, and then what you get basically in the ideal setting is like sampling complexity is like 3 over epsilon squared delta, where I haven't explained what epsilon delta is, but it's like basically the confidence interval of the estimator. So it's epsilon closed with probability 1 minus delta. Sorry. And yeah, to this you get this alpha correction. So to the 3 up here you get alpha correction. You can principally make this alpha correction like arbitrarily small if you're willing to pay this price here. But you can choose it as 3 points.
And is the epsilon on what quantity? On F lambda. And how is that the decay rate or?
I should have written this down. No, it's basically horizontal.
might.
So basically, it's a probability that basically your estimator F lambda hat.
No, that's okay. I just wonder, like, how precisely do I need to know this F lambda and what does it tell me about the physics?
Yeah. So how precisely you have to know it?
I mean, F lambda is that the decay rate of my, or the fidelity of my gate, or what am I meant? What?
F lambda, no, it's the thing that you want to fit. So this gives you basically error bars in the signal up here, right?
Okay. We want to benchmark the, sorry. But this is, I think it's important. We want to benchmark these gates, right?
Yeah.
We want to know the fidelity, I guess.
Well, if you like, yeah.
Okay. So, but is F like the fidelity, or I mean, like?
No. It's this signal here. Like every data point is such an F lambda of M. And then I vary M, and I get like multiple data points, but I have to estimate every data point statistically.
Okay.
Right? And basically, this just tells me that I have a confidence interval for every data point here. So how much samples do I need to get like a certain confidence interval? That's, I mean, yeah.
Okay, if I have like a quantum computer with gates that are really good, let's say 3 or 4 nines fidelity, how many shots do I need to verify this?
Well, in this setting, you would, I mean, to first order need a constant number of shots.
Okay.
I mean, for every M, then you have to do like at least a few M's to be able to do it. But you don't have to like measure out the full curve, right?
Okay.
To be able to do the experiment.
Because I think that's interesting to like go all the way and plug it in and see how many shots do I need to estimate the fidelity.
But yeah, I have to finish the paper at some point.
Yeah.
But there are also some other ways of doing this estimation, like doing it per point, but yeah.
Okay, thanks. Now it's clearer what we are actually talking about. Cool.
Good. Fine. So but it kind of closes the overview part of the talk, like the high-level part of the talk. So in summary, basically what we basically need is in the depth for this to work. But I mean, at least for universal radio circuit, but if you plug in smaller groups, you can actually get a very constant depth for some. Poly group, for instance, would be like a shame if you get that there. So one question is basically how does this compare to what people call linear cross-entry benchmarking and the quantum supremacy experiment? Because that's like still like an open question that I actually want to really know what the relation is, because they claim something like they need square root n depth so for their supremacy experiments. And I just cannot see how it works because I think you're still here in this regime. So your linear cross-entry is a bit too high, I would say. But
you're saying, sorry, I mean, wait, so you're saying that, I mean, there's many problems with circuits, right? I mean, if they're too long, then you get crushed in noise and so on. But you say that the trouble here is if you're square root of n, then you're not in the right regime to do linear cross-entry benchmarking altogether.
I mean, you're in a regime, but you might be overestimating the linear cross-entry.
Is this independent of the 1D, 2D circuit layout?
Probably not. It must be dependent on
because they have like a 2D circuit layout, right?
Well, but yeah, but I mean, this doesn't change the lower bound. Yeah.
No.
I mean, the spectral gap cannot get better than constant.
You tell me.
It does.
But then what does it mean? I mean, basically you're saying that they don't get the linear cross entropy.
Yeah, I mean, I'm just saying it's like kind of I don't understand how they are basically. I mean, I also looked at some works in this direction, but they seem to be content with like giving one norm bounds on the outcome probability. But then if you do linear cross entry benchmarking, what you do is you do this. You multiply this with dimension, for instance. So
That is okay.
So,
But I mean, of course, it's one thing to have this nice bound on the M where it kind of sets in, but there's another thing to make a plot and talk about this.
Yeah.
And I mean, the text is long, right? I mean, it's like 70 pages basically on linear cross-entropy benchmarking.
Yeah.
Not quite, but it's also not entirely wrong. And I mean, they have lots of plots of that kind. I mean, you kind of see with your eye when it's like linear, right?
yeah, exactly. That's the point. So, yeah, that's the point. It's a okay. So it's not totally clear what it means, and that's why I'm saying that I'm interested in clarifying this. Because I mean, I will not make any claims so far. I mean, it's just has to really like work on this.
Interesting.
But to put it in a different way, you're kind of saying that in the regime that they consider, you're not mixed enough yet in a way to apply the kind of standard AB kind of theory to it.
Yeah, so at least that you can doubt whether like it is enough.
Yeah, I see. Okay, just another question. Okay, no.
Yeah, maybe also on this front, like in this plot that you're showing in the upper right corner,
Yeah.
in the regime that's like before the dashed line.
Yeah.
Have you like how did you generate this plot? Like how did you see this non-exponential decay there?
Well, I mean, you can just like simulate it more.
So right, okay, that's why I'm asking. So this plot you got by simulating it.
Yeah, it's just simulating it first.
Right.
In Hilbert space.
Yeah. Yeah, I mean, just yeah, it's basically simulating the experiment.
Yeah.
So we also have some nice plots, and even if you don't have noise, right? It's what the green curve shows. Even if you don't have noise, there's like a regime where you're not constant. Yeah. So so you can simulate this. Yeah. And actually, there's a paper that actually simulated. So there's like a from summer there's like a paper that did this with clipboard circuits, not universal circuits, but with clipboard circuits, and did a couple of simulations with different random circuits and different noise models. And they also find that that's basically there's like a regime which is approximately linear and where things are not quite exponential.
But that means they're kind of too optimistic, right? Not too pessimistic.
Yeah, they're too. Yeah.
So that's I mean, in a way, you are the bearer of bad news, not good news. In a way, just to fix the sign.
Exactly. So I would like to clarify this relation a bit more, and I think it's yeah. There's at least some.
When we get this exponential decay curve,
Yeah.
how many information can we get about the noise? I mean, with this exponential decay curve, what can we do next?
Yeah, so basically from the decay rate, you have a single quantity, right? Like a single.
Maybe you have zero. I mean, zero eigenvalue. Also, you mean you only have one eigenvalue associated with it. If you have zero, I mean, you have zero eigenvalues or only single eigenvalues.
Well, I mean, if I understood you correctly, so the point is like, so you're kind of right. So the signal comes, so you get like a lot of contributions to the signal, and it's related to eigenvalues. But the point is like after like a while, you will only see the dominant one.
So you only care about the dominant one.
That's why you have this thing in the beginning. It's basically the contribution of the subdominant eigenvalues.
Okay, I see. So with main eigenvalues, and then you want to get the average fidelity of this.
Yeah. So traditionally people claim that this is related to the average gate fidelity, but they're like, I will not open this discussion. I mean, there are like many papers on this why this can be problematic. And I would just say it's a performance quantifier. So, and then let people.
Have you seen talk? Have you went on stage and talk for an hour?
Yeah.
Why?
I mean, I would let other people debate it, what it means.
Fine.
I mean, you can even like make this a bit more clear what it is and what it's not. But I think it will not go into this.
Yeah.
There was a question back there somewhere.
I don't quite understand the third point. So do you intend to change something like the frame operator?
Yeah, so basically so we have a section of our paper where we discuss this linear depth issue, and also in the linear cross entry benchmarking community. So there's like there have been like 1-2 papers about so they also kind of noticed that there's like linear depth or so they wanted to also change the post-processing linear cross entry to account for this, but it didn't in a kind of ad hoc way and not really well motivated. And so what we do is basically change the filter function, and there's like one way where we change frame operator. So we do it like shadow-like, and we use the like frame operator of the random circuit. And then this would give like basically perfect signals.
How do you define the frame? How do you define the frame operator?
Well, in a second I will show you.
Oh, okay.
So again, so are we now in the setting where we want to know the more technical details?
Oh, right.
Okay, fine, then we go on. So there's like a cute scroll, and then we go on.
The last
So
introduction.
basically, so the thing is basically already the noise-free setting is kind of like very illuminating. So recall that omega was what we call the representation. So it's a representation of the group on linear operators. And then without noise, what we just have is basically
The perfect world.
What?
The perfect world.
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 The perfect world. Yeah. In an ideal world, in the perfect world, you have this form probability here. And what you can notice is basically that, okay, while you have a basic measurement and there's some unitaries in front, so what you get is PWM. And associated with this PWM, you can define a frame operator. And this frame operator is basically simply, the channel twirl of channel M, which is the completely depolarizing channel in this basis. Yeah? And so you take this completely dephasing channel in the basis, you twirl it, and over this measure nu that describes the random circuit. And if your random circuit has depth M, you take the M-fold convolution of this measure. And so this will be the frame operator associated to this, to like a random circuit of depth M. That's what people for shadow estimation want to compute. So your tensor network paper, with what is like brickwork circuits, you aim to like basically compute this operator, super operator. So that's SM.
What does this mean physically? So you said that you're doing this for compact groups. So if I take the simplest compact group, let's say I take U1, what's going on here?
Okay, so basically, so this is a PWM, right? So basically, what the frame operator tells you is basically, okay, the frame operator gives you a reconstruction formula. So basically, if you measure in this PWM, and let's say it's informationally complete, and this means that this thing is invertible, and then you can use the measurement data and the inverse of this operator to reconstruct the state. That's basically how state homography works.
I see. Okay, that makes sense.
So that's the reason why I call this like, this is associated with this PWM. And also, if you recall, this the inverse of this operator popped up in like the filter function, basically for reconstruction.
But okay, but there in your filter function now there's two groups, right? There's the group over which you do the twirl to define your frame operator, but then there's the other group from which you take the irreps.
Oh, it's the same group.
It's the same group.
There's only one group but two measures. So basically, we have the bar measure, and we have our measure from which we actually sample instead. And then we, if we fill the random circuit, and we get M-fold convolution of this measure. And what we want is basically that this M-fold convolution converges to the R measure. And kind of, I mean, this is pretty generically the case actually. So what then happens is basically that this frame operator converges to the R measure.
So that's the condition on your measure.
Yeah, that's actually just it. I mean,
in the beginning you said almost every.
yes.
That's
So you're not
referring to
allowed to do
this.
stupid things. That's the assumption. It's basically that, right?
And
But you have to avoid this.
okay, yeah.
Anyway, so basically you have this convergence from this frame operator to this frame operator. And this is what you see in the signal. That's my point.
That's
So
very,
yeah.
I'm a bit slow with this. The number of convolutions, is this group dependent?
No.
It's group independent.
Well, yes, a priori you can take, can do convolution as often as you want.
No, but like you have a certain number of convolutions until you converge to the hard measure, right?
Yes, this can depend on the group. Yeah.
This will depend on the group. Yes, okay.
Depends how basically, it's basically a random walk that you're doing on the group. And I mean, how fast whether you depends on the group, how big it is and everything. Yeah.
So when you said you wanted to achieve sublinear depth,
Yes.
you meant by changing the group such that you decrease the number
No,
of convolutions.
I meant by changing the filter function. So basically,
Yes, but the filter function is also dependent on your frame operator, yes.
yeah, but I can change the definition of it.
Oh, I see what you mean.
Yeah.
Oh, I see.
Yeah.
Okay, that makes things clear.
So basically, in this definition that I showed you, if you look what happens on expectation in the noise-free setting, you write everything out. The filter function is this thing, yeah. The bound probability is then from the right. And now I mark some terms, yeah. And this is the frame operator. So you plug this in, and then you will basically see that what in the noise-free setting happens is you will see s to the minus 1 times sm. And if you increase m, then this converges to the identity.
I see.
And then you will what is left is basically the overlap of your state with the error.
And why can't you put Sm to the -1 instead and be happy with
That's
it?
what we propose in paper. And so if you write here Sm instead of s to the -1, then you would for any finite m would have the identity there, and then it should in principle work better. That's what people do in shadow estimate. Yeah? But then you have the problem that it's hard to compute Sm, for instance. And we haven't analyzed this setting in the paper, and it's even a bit worse. We need some more new techniques to analyze the setting actually. But it's not easy to say in like 2 centimeters, but I'll try it. Yeah? It's just you would come up with new techniques to analyze this kind of. Okay. And yeah, this convergence you see in the green curve. Yeah? So basically, the convergence to a constant that's exact loops exactly what's happening here. There. Okay. And right. So now you can ask basically how fast does it converge? Because it tells you basically where this gray line lies. And the convergence rate, so we call this as Sm, and for the convergence rate, we look at this channel curve. So we just look at we ignore the m in the middle and look at the channel curve. And because we have a p lambda from the left, we actually we can restrict one of the representations, like one on the left hand side on Golden error. And then we have like a kind of like a protected channel curve. Yeah. And the nice thing is that this thing has like a nice form. Namely, it has like a one component here, the block diagonal 1, and something which is strictly less than 1 in spectral norm down here. And this is exactly the spectral norm of this block down here is exactly 1 minus the spectral gas of this spectrum. And so basically the convergence rate that determines what's happening here is basically given by the spectral norm. Spectral gap.
Okay, but that's not saying anything yet about the setting in of the decay.
Well, it implies something. Yes, it's right. But you can basically if you do this, basically you can now separate Sm into like S plus something.
Okay,
Yeah,
fair enough.
and the something comes from this block.
Yes.
And then the S part will give you the constant already. And the part down here gives you like a correction.
Yes.
And how fast the correction goes down is given by the vector.
I see.
This tells you basically when you have to draw this. So that's okay. Okay, so but we have noise, right? And so how we model the noise by using a concept that's called implementation function. So first of all, we replace initial state and measurement by some noisy variance, and we replace the representation by this implementation function. And this implementation function, well, it can be basically anything. We just assume that it's like completely positive on every element of the group, and we trace on it.
But is this a typo, gate dependent, or mean gate independent?
It's gate dependent, like it's phi of g. So every g is a different phi.
Okay.
Yeah. But what we cannot model in this way is like non-Jacobian noise, because it's phi of g and not phi of what happens before g. And you also need time stationary noise, because there's no time when it's in function now. But aside from this, it's so far very general. And what we then do is basically perturbation theory. And for this, we have to assume that the perturbation is small in some sense. So this means that basically this phi is not too far off from omega on average. Yeah? And if this is true, then what we can do is basically now we have, instead of this channel twirl, we have like a noisy channel twirl where basically we replace omega by phi here. And what we can show them using some matrix perturbation theory is basically if phi is sufficiently close to omega on average, then there is a basis change such that this thing is block diagonal. Yeah. And now the upper left block is not 1, but it's some I, a scalar so far, and down here there is some matrix O. But you still have guarantees for these blocks. For instance, that this block is less than 1, and the spectral norm of this block is less than 1 minus the spectral gap plus the calibration error. So in particular, this is still smaller in norm than this. And if you increase the noise, then this will generally break. So basically, then at some point, these blocks will start to mix, and like all kinds of weird things can happen. Yeah.
Just a question, like if I understand correctly, essentially you're replacing the representations of this group with a different function.
Yes.
But does this, like, do you need the noisy gates to also form a group to do this, to have this sort of noise representation? No. Okay.
It's just you can just see it basically. I mean, if you like, it's just the representation and the noise channel associated with one.
I see. Okay. Yeah. Yeah.
It's also like this works by Joel Warman, where they have this like noise in between gates or something like this. It's more or less equivalent to this approach. That's different.
Okay. Thanks.
Yeah.
But is this okay? I mean, I don't know, but is this analysis basically kind of the same as in the Helsen paper, or is this different?
Well, up to here it's the same, basically.
But the perturbation theory is different.
The perturbation theory, I mean, we use the same theorems, but we use it
in a different
level.
Okay.
Because in the Helsen paper, they have this inversion gate. So they have basically
that's true, yeah.
You have to basically put in the Fourier transform by hand, and it's inverse. And by filtering, we get the Fourier transform for free, basically. So we see the channel directly, and this is like a standardized Fourier transform. And so we don't have to. It's similar. So the point is also, that you will probably get the same decay rates both protocols. If you do inversion or not, so to say. It's kind of universal.
And I mean, this perturbation, I mean, in our, what do you call it, paper, I mean, you also got the perturbation theory, right? I mean,
yeah, it's the same perturbation theory.
It's the same.
Yeah. So it's two inside. Yeah. But the point is now that the same thing happens as before. You get a contribution per block. And this thing is the dominant contribution because, well, this is the subdominant contribution. And you ask when is the subdominant contribution gone. And this gives you basically another criterion like before. And the dominant contribution will be exactly this exponential decay. So that's the point. Right, because it's like less than 1 in general, we could do a real decay. Actually. Already talked for almost an hour. Sorry. Okay, so I think I will not explain how sampling complexity works. It's really similar, but I think I will not. But I think what's interesting is that basically what happens if you have multiplicities, because it seems to be that people are now trying to construct examples where weird things happen in RB, and so far I have implicitly assumed that all errors are multiplicity free. I probably you haven't noticed, but it's also for presentation purposes. And the thing is basically the same thing works if you have error appearing multiple times. Yeah, and but the difference is basically this block up here is not a scalar anymore, but it's instead a matrix. And it's exactly an n by n matrix, where n lambda here is the multiplicity of the error of lambda. And then what you see instead, there's some guarantees. Instead, what you see is not exponential decay, but a matrix exponential decay, and this is also in the help in your paper. But the bound of M is exactly the same. It doesn't depend on the multiplicity. Yeah. But what
how does this technically work? It's it's not to me the whole
the filtering is the. I mean, well, in principle, it's because like this spectral gap bound or the spectral norm bound on this lower right block doesn't depend on the multiplicity. That's the reason.
Okay.
And there are also no factors popping up that depend on the multiplicity. That's the reason. And yeah, but in principle, if you have multiplicities, then you can get weird signals which are not exponential decays, because this is a real matrix which might have complex eigenvalues, and then you will see the oscillations in the signal. And that's apparently what people are trying to observe.
What does spec of I lambda mean?
The spectrum, the eigenvalues. I mean, this is the.
But you said they can be complex.
Yeah. So the modulus of the eigenvalues is in signal, and in particular the real eigenvalues. Okay, so that's yeah, sampling complexity. I'll just jump over it. It's not so important. So yeah, thank you.
maybe you can get you can guard yourself one sentence on the sample complexities. It's good to step back 1 second, but it's less than a second. Then
yeah, I think that the basic insight is that if you look at the second moment, it's similar in the first moment if you write it out, and you can do perturbation theory again. And somehow this is what currently. So the only thing what happens is that you get more errors now, and this means more of these dominant terms. And you have to work a bit harder to all subdominant terms. So that's the.
And do you get do you retrieve, let's say, the sampling complexity bounds that are known without overhead, or like, yes. at the okay.
So also like the ones from federal estimation.
Yeah.
Because our scheme works perfectly well if you take hard in the case, right? And then it's just spectral gap is 1, and it works perfectly fine. You recover everything you know from these papers.
Nice,
yeah.
Of course, you don't like, you need to know. I mean, we have this one project where you need to know the projectors. Like, you need to know the projectors to do the filtering.
Yeah.
If you don't know the projectors, then you can't do this.
Yes, you have to know your representation.
Yeah.
Yeah, that's right. I mean, we also have like 1 or 2 ideas where we don't know the representation theory too well. So,
On that note, we start a book club on representation theory.
Yeah, but I think this is like not known. Or like it's like representation theory, which is not because you just don't know it; it's just not known, perhaps.
yeah.
No, but it's not.
Yes.
Yeah. It's not a mathematical problem. It's just a.
Oh, yeah.
But also, if you look at Jonas' matchhead paper or so, I think there's like, I mean, there are like a couple of pages where he looks at representation or Arabs. It's just what you have to do in general. Yeah.
Sorry, this might be a very stupid question, but I sort of lost something in the meantime. It's like with this technique, you get this exponential decay, and you get 1 exponential decay for every Arab of your group.
Yeah.
Like why? I mean, why are you interested in treating the Arabs separately for the noise?
Well, I mean, the point is, I mean, you don't have a choice.
Okay.
So basically, what you're more or less doing with this randomized protocols is you perform these like channel twirls, and basically in the channel twirl you will see the errors. That's just representation theory. So they pop up if you like them. And basically, if you don't do the filtering, they will pop up all at once. Then you don't have to know the projectors, but you will see basically a signal which is composed of a lot of contributions, and it's hard to isolate the individual contributions. And if you do filtering, you will see every contribution isolated. That's the.
Okay, so for example, you might find examples of group where just 1 Arab is the responsible for all the noise or something.
Yeah,
like this.
so what we're doing right now, we're writing a paper for instance crosstalk randomization, and there basically you can associate the Arabs to basically basically to subsystems. Yeah.
Mm.
And so basically on the gates are acting on this subsystem non-trivially, on all of the others trivially, and then you can basically use this to benchmark crosstalk between individual subsystems. Also, the filtering is also basically Arab dependent, so you get Arab dependent constants. So basically, which if you do the global thing, you will only see the global dimension, and here you see the Arab dimensions. This means that basically sometimes you're in a situation where you have small Arabs and big Arabs, and you can efficiently do things for small Arabs, but not for the big ones. Okay.
Yeah, I mean, of course, I mean, it's just if you have more decays, then it's a pain to recover.
So also in terms of efficiency, basically. So this happens, for instance, for this crosstalk thing. Basically, if you want to know crosstalk between all qubits, then it's difficult. But if you only want to know crosstalk between, like, I don't know, every pair of qubits, then it's easy.
I see. Speaking of crosstalk, I mean, we have the crosstalk example in our like shadow channel paper. How does this compare? I mean, in this kind of running papers that they're measuring, there's also a crosstalk example in.
Like it's single qubit.
Yeah.
It's a similar answer. It's the same thing as in this Gambetta paper from Simultaneous RB. I think it's that one from 2012. So they already sketched this idea there. So, it's basically the same, I think. But there was also a question.
Yeah, I just want to ask a more general question. So at the beginning, you were saying that this exponential decay is kind of universal, and it's important that this decay rate is somehow meaningful.
Yeah.
So I was wondering, in this case, this I, is there some way that I can sort of interpret it, or what makes you say that it's meaningful?
Well, I'm saying that I know where the I comes from in the sense it's meaningful. Because I can guarantee you that the I has a certain form. And I can also write down a formula for the I. So basically, so because there was this question about average gate fidelity and so on. And in principle, you did things something like an average gate fidelity up to some corrections. And you can actually make this explicit. Basically, that's what I meant.
Okay, thanks to this form. Basically, thanks to this formula, you can
thanks to the perturbation theory, everything, you have this explicit formula on where this comes from.
A technical question, if you allow me. You mentioned this paper about the randomized benchmarking for match gates by Hansen. That is scalable, right? Because the filtering you can you don't need to you can simulate actually the match gate circuit. But it fits in your framework, right?
Yes.
But your condition on the frames, you know that when you sample each gate independently in this M-fold product of the measure, this must converge to the hard measure of the group.
Yes.
Okay. In the match gate case, you know there is it has a hard measure that you sample this special orthogonal matrix, and then you calculate the associated match gate circuit. So this means that if you just sample the parameters of each match gate independently, this will go to the same distribution as if you just sample, you know, the global special rotation. That is the way you generate match gates uniform. I don't know if the question is.
If I understand it correctly, if I understand it correctly, that the question doesn't really depend on match gates, right? It's more the question whether you sample from something and then you compile it.
This is your condition, right? But I know that in that case work, right? Then in that case it should mean that or just by chance. I guess it is the case, right? That if you
it's a generic feature, so basically if you can either like sample and then basically construct a circuit, or you can
but this
define a circuit and then convert to the.
But it wouldn't be easy to prove, right? That you would that it would be distributed the same way if you just sample individually the parameters of each match gate, or if you first sample, you know, the global.
Yes, I mean
matrix that it's associated. You know what I mean?
You have to have some bounds on basically on how this distribution converges. Yeah. So that's in our case it's the spectral gap basically that quantifies how well this converges. And you have to know at least you have to have at least an idea like how big the spectral gap is. Yes. But it's basically the price that you pay for going like bottom up instead of top down.
And okay, I'm not so familiar with this, but I guess getting these bounds is not that easy, right? In general.
Which bounds on spectral gap?
Yeah.
Well, the good thing about the spectral gap is that there's like a rich literature on it. So there's like mathematical literature on random walks. There is like quantum info literature on random circuits, and there's like many body literature on like spectral gaps of Hamiltonians, and so there's like really like plenty of techniques that have already been used successfully to prove bounds on spectral gaps, and even if you're not like, I mean, there's still on top there's some lemmata you can use to basically promote bounds on like similarly looking circuits to one that's actually of your form and stuff like this. So there is a tool set. I mean, it might be the case that like for your random circuit, it's hard to get bounds.
Yeah,
that could be the case. Yeah.
You basically just go to Jonas, ask him.
Yeah, you should go to Jonas indeed.
And then if he can get you the water spectral gap.
So I don't know, like someone who knows that shit, But it's, I think on a scale of difficulty, I think the spectral gap is one of the nicest things when it comes to conversions.
And you had this blue-green slide with the green new things, and you had, I think, targeted. What was the same? What do you mean by targeted exactly?
I mean that basically the goal was to isolate these error components. That's what I meant by targeted.
Okay, and that's new.
No.
Okay, right.
The new thing is that we proved that it works.
Yeah.
So basically, so in Jonas, Emilius,
because you also
did your paper and Albert, I think there is you proposed this filtering idea, but basically. So basically, the analysis of the approach was limited, let's say, yeah. So what we did is basically we filled in, all the details.
Yeah.
Basically, the idea comes from this.
That's actually what you do, and in the end, it's the same still, right? That was what you said.
Post-processing is the same. Yeah.
Cool. Thanks.
What what the biggest thing that we changed is basically the assumptions of the measure on the sampling. Because in this paper, then needed basically the measure is close to the H measure and total variation distance. And here we only need it close in moments.
And I think we are talking about. I think you are talking about two different papers. I feel. I think you're talking about the.
I'm talking about just to mention the framework paper.
Yeah, I think
The mother paper.
I mean,
yeah, but
it was involved.
No, but the filter was in the mother paper.
yeah,
It was the first mentioning of
but
it.
it's but
The filtering has even the no
anyway,
end.
anyway, yeah, it doesn't matter. And the other one,
Doesn't matter.
you only assume like flip-flops, like you don't even go to like anything which is
It's like random sequence.
yeah. And there you don't have so much difficulty proving the stuff.
Yeah, but there's also only get independent noise in it.
Yeah,
And uniform sampling.
exactly. It's much simpler setting.
Yeah, exactly.
Yeah.
Wonderful.
Still around for a bit if you have like more detailed questions, and there's
Yeah, we had three parts. We had the introduction part. No, four parts. The introduction part, the squirrel part, the technical part, and then the very informal part. I think let's start with the very informal part, but for that we switch off the camera and then we select the speaker again. Very good. Thank you.